Hi, welcome back. So today we are going to see another interesting topic called stoichiometric air-fuel ratio for diesel fuel. So in engine theory, the stoichiometric air-fuel ratio is a fundamental concept. It is the exact mass ratio of air to fuel where there is just enough oxygen to completely burn all the fuel, leaving no excess oxygen and no unburned fuel in the exhaust. Have you understand? So simply I can explain that we have a fuel and we have a air. When it mixes together and it will burn completely without no traces of any unburned fuels. Okay. So the amount of fuel required for combustion is air, right? Okay. So for combustion, the air is the important quantity. Okay. And how much quantity it is. So correct quantity means it is called chemically correct mixture. Correct quantity means it is a chemically correct mixture. That chemically correct mixture is only called as stoichiometric air-fuel ratio. Okay. So what is stoichiometric air-fuel ratio? When the fuel wants to burn completely with the proper amount of air. Okay. So that calculation today we are going to discuss about. Okay. So for typical diesel hydrocarbon like cetane, this ratio approximately 14.5 is to 1. So how this value arrives? How this value arrives 14.5 is to 1. That is what today we are going to discuss about. So this 14.5 is to 1. It tells about 1 kg of fuel requires 14.5 kg of air. Okay. So this means for complete combustion of a diesel, it takes about 14.5 kilograms of air to burn 1 kilogram of diesel fuel. This precise ratio comes from the balanced chemical equation of combustion. Okay, so now here see the atoms on the left from the fuel and the air. Okay, fuel from the fuel C12H26 is the fuel, 18.5 O2 is the air. Okay, must equal atoms on the right in the products. Okay, when this brought to combustion, this is the product, right? Okay, so now this should be balanced. This should be a balanced. Okay, how this balance comes? Okay, through this balancing only we will come to know about the stoichiometric air-fuel ratio. Now see here, this is a pure chemistry. Okay, but in real diesel engine we almost never operate at this stoichiometric point. This is important. Okay, we almost never operate at this stoichiometric point. Excuse me. The defining characteristic of diesel combustion is that it is inherently and intentionally lean. Diesel engines always operate with the excess. Yeah. Okay. Why always lean? Why we will not run at stoichiometric in diesel? Okay, that is another important question, right? Okay, the answer is in a diesel engine, the fuel is injected into a highly compressed air at the end of the compression stroke. We control the power output solely by varying the amount of fuel injected. Amount of fuel injected. Okay, while the amount of air drawn per cycle remains relatively constant. the amount of cycle, the amount of air the amount of air drawn from an engine, okay, per cycle is relatively constant. Okay, so there is far more air in the cylinder than stoichiometric amount needed. for the injected fuel. Is it clear? Now this is the question. This is the answer for the question. Why always lean in diesel? Okay. There is far more air in the cylinder than the stoichiometric amount needed. Okay. For the injected fuel. Okay. This creates a global lean mixture with the air-fuel ratio commonly. So this air-fuel ratio commonly ranging from 18 is to 1 is at high load. 18 is to 1, 18 is to 1 is at high load. And to as high as 80, okay. 80 is to 1 at idle. Okay, at idle, the huge amount of air is required. Okay, to overcome the see, listen, the engine is developed, the engine is designed to develop certain amount of power even if it is idle. Okay, so if it is idle, the engine has to produce that certain amount of power, right? Okay, so for that it requires a more amount of air. Okay, so now we are going to calculate the stoichiometric air-fuel ratio for diesel. So as shown the chemical equation of in the previous slide for diesel C12H26, and then the molecular weight of the carbon, hydrogen and oxygen is given in the right hand side here. So in the left hand side of that equation we are going to take that, for example, C12, so 12 carbon atoms into the molecular weight is 12, so 144 gram per mole. The same way we are going to do it for hydrogen and as well as oxygen, and then for air. So for in the air, 23.2 percentage of oxygen is by mass it is available. So we are going to convert that into mass of air required. So 2552 gram of air is required. So now we are going to calculate the air fuel ratio for that diesel. So it will give 14.5 is to 1, which means 14.5 gram of air is required to burn 1 gram of fuel. Okay, or we can say it as 14.5 kg of air is needed to completely burn 1 kg of diesel fuel. Okay, so with this we are going to stop the stoichiometric air fuel ratio topic. In next videos we are going to see some good video related to the engine. Okay, thank you.